Okay, this video is going to be for demonstrating how we can connect motion in rectangular coordinates to motion in angular coordinates, as well as angular velocity and linear velocity. So if we think of writing some r vector as x I hat plus y j hat plus z k hat, right? And then we want to assume that we're going to rotate around the z-axis. So let's imagine this is our xyz coordinate system. We've got, this is our r vector here. Its distance from the z-axis is this thing we'll call big R. And the angle that makes, we can, with the x-axis from the vertical is theta. So let's imagine that this goes down here like this. This is our r, and this is our theta. So that means that x is r cos theta, y is r sine theta. And we could write this in terms of some other angle to do for z, but we're going to not do that here because we don't really need to know that additional angle. So we're just going to call our z. So this is a cylindrical coordinate system. And so cylindrical coordinates are r theta z. Okay. Spherical, we would replace that z by a phi, but this is a different radius here. Okay, so notice that our big R is not the magnitude of our little r vector. It's a different radius. Okay, so now we can write our r vector as big R cos theta I hat plus sine theta j hat plus z k hat. Okay. Now, our velocity then is dr dt. It's always true, right? And now if we are only undergoing rotational motion here, then that means that our big R, is constant. Our z is constant. And our theta is the only thing that is a function of time. So we've got theta of t. Okay. So now if we take the time derivative of this thing up here, we've got dr dt is big R, which is not a function of time, so my derivative just goes inside that, d dt cos theta I hat plus d dt sine theta j hat. And that's it, because our z is not a function of time, so that derivative is 0. Okay. And then the derivative of cosine is negative sine, so this gives us r negative sine theta I hat plus the derivative of sine theta, which is cosine, so cos theta j hat. Okay. Now notice that this thing has, times d theta dt, sorry. Okay, so the derivative of cosine theta is negative sine theta d theta dt, right, by the chain rule. And the derivative of sine theta is cos theta d theta dt. So that's why I have this d theta dt on both. Okay. Now, d theta dt that's omega. That's our definition of omega, right? And r is a constant. So this dr dt, which is v, is r omega negative sine theta I hat plus cosine theta j hat. Now notice this part of the vector has a magnitude of 1. So this only has to do with the direction of that vector, okay? And the magnitude of that v is constant and is equal to r omega. Okay. Well, it doesn't have to be constant, but it's always, it's whatever omega is at any moment in time, even if theta is, even if omega is changing. Okay. All right, so that is for velocity. And now let's think about acceleration. So our acceleration is dv dt. So now we've got r omega negative sine theta I hat plus cos theta j hat. We want to take the time derivative of all of this. So our r comes out again. So we've got r. And then we've got d dt of negative omega sine theta I hat plus d dt omega cos theta j hat. So let's consider each of these terms independently, because this is starting to get to be a little bit of a mess to do it all at one time. So the time derivative of negative omega sine theta, we're going to want to use both the product rule and the chain rule. So this is going to be negative d dt omega times sine theta plus negative omega d dt sine theta. Okay. And notice that this thing is alpha. d dt of omega is just alpha. Okay. So we've got negative alpha sine theta plus negative omega. And then the derivative of sine theta, we need the chain rule. So that is going to be cosine theta times d theta dt. And this thing is another factor of omega, right? So we've got negative alpha sine theta minus omega squared cosine theta. That's our x component, our I hat component of our acceleration, right? And then now let's do the same thing for y. So we've got d dt omega cos theta is d omega dt cos theta plus omega d dt cos theta, which is d omega dt cos theta plus omega negative sine theta d theta dt. So we've got alpha cos theta minus omega squared sine theta. Okay. And now let's plug both of those into our A above. So our A then is R times alpha cos, negative alpha sine theta minus omega squared cos theta I hat plus R times alpha cos theta minus omega squared sine theta j hat. And then let's rearrange some terms and see if that helps us make sense of this. So we're going to put all the terms with r alpha on them together and all the terms with r omega squared together. So we've got r alpha times negative sine theta I hat plus cos theta j hat. And then we've also got a minus r omega squared cos theta I hat plus sine theta j hat. All right. So let's see if we can make sense of either of these terms. Okay. So this second one, cos theta I hat plus sine theta j hat, that's just r again, right? So this second term is negative r omega squared times our r vector. And so that is our centripetal acceleration, right? This has exactly, this is not actually the r vector, it's a unit vector in the direction of r. Let me erase, I wrote this wrong. This is in the radial direction. You can think of this as big R hat. apologies, it's not in the little r direction, it's in the radial direction. So if we look at from above, if this is our r, if we're looking from above in the xy plane, if this is our r vector, this thing is in the direction toward the center of that circle, okay? So this is our centripetal acceleration, and it has the same magnitude as the centripetal acceleration we found in previous chapters, right? And then this part points in the v direction, right? To see that, put a line between these two parts. To see that, we can go back and look at our v vector from before. Remember, that was r omega negative sine theta I hat plus cos theta j hat. And so the v direction is, we could also think of it as the tangential direction. So this is the tangential direction that points along the direction of travel. So if we imagine here, well, I'm getting crammed. I'm going to draw the overhead view again because I didn't leave myself enough space. So I'm at this position, r, got some angle theta, I'm looking above my xy plane. Let me actually draw this so that my xy plane is here. Xy, r, this is theta. This thing is going to undergo circular motion like this, right? That r vector points like this. The v vector points like this, v. Okay, points tangential to the circle. Points tangential to my circle, okay? So this last term we're going to call the tangential acceleration, and that points in the tangential direction of the circle. And this other term we call the centripetal acceleration, and it points toward the center of the circle. And so these were what we would have expected. And the magnitude of the tangential acceleration is r alpha, or r d omega dt, or r d squared theta dt squared. And the magnitude of our centripetal acceleration is r omega squared. All right, and that's the end of that part.